Hi you guys, we're going to do a little bit of work with 3.6 today. Turn on some lights. Here we go. Mr. Shadio asked me to put together some notes, and I thought it would probably be just as easy. I started writing all this stuff out, and I thought, well, let's just do it. So 3.6, first thing in the notes is a bunch of formulas. And you can read, so you can see the differences in the formulas, and we're going to talk about, as we go through the problems, when we use which formula. So, problem number one, definitely going to need a calculator, so get one out. Number one, suppose we invest $500 at 7% interest compounded annually. Find the value of the investment after 10 years. If you look up at the very top of your page, it says, if the first formula at the top says interest is calculated at the end of each year. So that would be annually. So that formula is this. Where P is the principal, R is the interest rate expressed as a decimal, and N is the number of years. A is what we end up with. So this is the beginning value of our investment. This is the ending value. Now, before we go any farther, I want you to look at the next formula. This is the formula for interest compounded monthly, daily, yearly, whatever, however many times a year that interest is compounded. Now remember, this one was once a year. This was at the end of every year. So if we looked at this formula, there's your principal, there's your investment, there's your interest rate, same thing. Now K is the letter they use for the number of times per year that we compound our interest. Okay? So, and that's a K there too. Those are the same K. Anytime in a formula you have the same letter, it means the same thing. So if we're doing quarterly, then K would be 4. If we're doing monthly, then K would be 12. Well, then T is the number of years. Okay? So I want you to look at what was happening over here. Over here, we were compounding at the end of every year, so annually, one time per year. So look what happens if you let K be 1 time per year. Isn't that formula exactly the same as that one? Now, I've got a T here for years instead of an N, but isn't it the same thing? So I really don't want you to think about these as being two separate formulas. They're not. That's this formula if K is 1, once a year. So for problem number 1, this is the formula we're going to use. I want to know how much I'll have if I invest $500, that's my principal, at 7%, 0.07 to the 10th power because I am waiting 10 years. So I'm going to figure this out on my calculator. So 500 times 1.07 raised to the 10th. Looks like that investment's going to be worth $983.58 if I round it off to the nearest cent. Okay, now let's look at the next one. Roberto's investing $500 at 9% compounded monthly. So that's this one, right? This is compounded monthly. So my investment is $500. My interest rate is 9%. Remember, you always put it in as a decimal. Divided by how many times a year? 12 times a year. Monthly. 12 times a year. Raised to the 12 times 5. Remember, your exponent is 2 things. It's the number of times a year you're compounding times the number of years. So 60 up here. So type that in on my calculator, and I would go ahead and make that a 60. I think it's easier to type it in. So 500 1 plus, don't forget parentheses, so 500 parentheses, 1 plus 0.09 divided by 12, raised to the 60th. I think that investment's gonna be worth $782.84. All right, number 3. Judy has $500 to invest at 9% annual interest compounded monthly. How long will it take for her investment to grow to $3,000? Now, we are compounding monthly, so we're using this same formula. This is the formula for compounded monthly. But now things are a little different, because now we know we want to end up with $3,000. And we're going to start with 500. Remember, this is your ending amount. This is your starting amount. Okay? 1 plus my interest rate is 0.09. I am compounding monthly, so my K is 12 again. Raised to the 12 T. I don't know T. How many years will it take? Okay, so let's see. I need to solve this thing. There are a couple of things I could do, a couple of ways I could go, but I think the first thing I'm going to do is go ahead and divide by this 500. So when I do that, I think I get 6. Now, guys, it's kind of late. I'm tired. I'm probably going to make some mistakes. Just bear with me. You're smarter than I am. You know, it'll be fine. How in the world am I going to solve that? Well, when I have to solve for an exponent, the way I probably ought to do that is to take the logarithm of both sides. So I'm going to take the logarithm of both sides of this equation. Now, the reason that we do that, you've just spent several sections talking about the properties of logarithms. The reason we do that is it pulls the exponent off in front. So we have the log of 6 equal to 12t times the log of 1 plus 0.09 divided by 12. So when I took the logarithm of both sides, this guy comes out here. And now to get t by itself, that's what I'm solving for, I need to divide by this 12 and by the log of this parentheses. So I'm going to divide both sides by that. Okay? So you do it however you want, but I want to caution you, there's 2 things down here in the denominator that you're dividing by. So they both have to be divided. So what I'll do is I'll do log 6 divided by 12. Okay, so I've got this part taken care of. And then I'm going to hit divided by. So I hit log 6 divided by 12 equals. And now I'm going to divide by the log of 1 plus 0.09 divided by 12. And it looks like it's going to take about 19.98 years. We did not need logarithms in our other problems that we've done so far because we were just straight typing them in. When you have to solve for an exponent, you're probably going to need logarithms to do that. All right, let's try the next one. Stephen has $500 to invest. What interest rate compounded quarterly is required to double his money in 10 years? Well, guys, it's this formula again. Anytime you are compounding monthly, daily, quarterly, whatever, compounding, da-da-da, this is your formula. So we want to double our money. So we want to end up with 1,000 since he's starting with 500. Our interest rate, we don't know. R It's compounded quarterly, so it's going to be over 4, raised to the 4 times 10. Digest that for a minute. I know I'm doubling my money, so I want to start with 500, then end up with 1,000. Don't know the interest rate, but I know it's 4 times a year being compounded, and the number of years is 10, if I'm reading the problem right. Okay? So let's divide by 500, so that'll be 2. Don't you even think about using logarithms. We use logarithms when our variable is up here. You know what your exponent is, it's 40. Now, you gotta get rid of it. You gotta get rid of it. So we're gonna take the 40th root of both sides, which is the same as raising it to the 1/4 power. Excuse me, 1/40th power. Because if we 40th root a 40th power, it's going to cancel. And it's going to leave me with 1 plus r over 4. I like to, instead of messing around doing the 40th root, which your calculator will do, I like to just raise to the 1/40th power. So this is gone. I have 1 plus r over 4 equals 2 to the 1/40th, so 2 raised to the 1/40th power is about 1.077. I'm not going to write that down. Well, I guess I will, but you know, I'm not going to round it off. It's right there on my calculator. But now this is my equation, because I essentially 40th rooted both sides. So that left me with 1 plus r over 4, and then 2 to the 1/40th power. So now I'll subtract 1, so the number on my calculator, this guy right here, I'll subtract the 1 and times by 4. So that interest rate, oh my gosh, I gotta double check and make sure I did that right, because that interest rate turned out to be 31.1%. That can't be right. Let me try that again. There, that's much better. Yeah, I messed up. Let me write down what I got this time. So 2 raised to the 1 divided by 40. Okay, I wrote that down wrong. It's 1.017. Da, 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 da. Okay, so then when I subtract 1 and times by 4, I get 6.9%. That actually is almost 7%. That rate is 7%. So it takes a 7% interest rate to double your money in 10 years, compounded quarterly. Divide by 500, 40th root to get rid of the exponent. Subtract 1, multiply by 4, and it's 6.99 something was that interest rate. All right, number 5. Suppose we invest $100 at 8% compounded continuously. Okay, turn back. We haven't used that formula yet. If you look at your list of formulas, you have one for interest that is compounded continuously. And that's what Mr. Miller finally called the PERT formula. That's your PERT formula, compounded continuously. A is still the end amount, P is still the beginning amount. There's E, the basic, that Euler's constant, your interest rate, and your time. Okay, so let's see. She invests $100, compounded continuously at 8%. Find the value of her investment at the end of each of the years, 1, 2, 7, and whatever. I'm not going to do all those. Let me just pick a random one. Let's do 5. At the end of 5 years. What is the value of her investment at the end of 5 years. Okay, I just picked 5. They want you to do 1, 2, 3, all that. We don't need to do all that. We just need to know how to use this formula. So, start with $100, 8% interest, 5 years, compounded continuously. So I'll just type that in on my calculator. No logarithms necessary, just type it in. 100 e raised to the 0.08 times 5. I got $149.18. Okay. 6. Ursula invests $2,000 with the bank at this much interest compounded quarterly. What is the equivalent annual percentage yield? Okay, well, let's go ahead and figure out how much she ends up with her investment. So she invests $2,000. 5.15 interest, so 1 plus 0.0515, compounded quarterly. What is the equivalent annual percentage yield? So we're going to let t be 1, so my exponent is just going to be 4. Okay, so I'm going to figure this out, see how much she has left. So 2,000, parentheses, 1 plus 0.0515 divided by 4, close parentheses, raised to the 4th. So she's going to end up with 2105, basically 0.01, I guess, if I rounded it off. Now, your annual percentage yield, if you look back here at there's a little blurb in your notes about it, says, it's the percentage rate that compounded annually would yield this same return. So I erased it, but our compounded annually formula is A equals P, 1 plus R to the nth. That's your formula? Or I don't know, is that an N or a T? Yeah. Okay. So I know I want to end up with 210501. I know I'm starting with $2,000. And I know I'm doing this for 1 year. Remember, we did this for 1 year. It was compounded quarterly, but only for 1 year. So now I'm figuring out what interest rate would give me that same yield, that same result. Okay, so what am I going to do? Well, I think all I need to do is take that number, which is still on my calculator, so I'm just going to take that number and divide it by 2,000. So if I divide that by 2,000, then that equals 1 plus R. So I'll subtract 1. And that interest rate, or that annual percentage yield, is 5.25%. Now, what that means is, and this makes perfectly good sense if you think about it. Remember, the interest rate they gave me at the bank was 5.15, but they were compounding that interest 4 times. So the effective yield of that was 5.25%. At the end of that year, I had actually made an interest rate of 5.25, even though the advertised rate was less than that. The compounding made that difference. So I hope you can imagine that if we were compounding monthly, that this would be even a little higher. Because the more times your money is compounded, the more money you're going to make. It's not a huge difference, but it is a difference. All right, good deal. Let's see what's next. Okay, number 7. Something is different about problem number 7. Okay? Read it carefully because there is something very different about it. In all of the problems we've done so far, we have walked down to the bank, handed them a chunk of money, and come back 10 years later or 5 years later or 1 year later, whenever, to see how much we had. That is not what's happening in this problem. In this problem, she is making regular payments into the account. She is saving, if you read it, she is saving for her future. So it's like your parents might have a college account for you. They certainly have a retirement account for themselves. I have a retirement account. So I'm paying money every month into that account, hoping that it's going to build up, to a decent amount so that eventually someday I can retire, right? Well, let's see. I need a new formula then, because none of the formulas we've talked about yet account for that regular influx of money. So let's look back at our formula list. We have 2 formulas that incorporate the idea of payments. One is future value, one is present value. Now, here's the difference. If you are saving for the future, in other words, if you are accumulating money in an account, saving for the future, you are going to use the future value formula. Now we'll talk about how it works and all that in a minute, but you're going to use the future value formula. If you are paying off a loan, because there's two ways to make payments. You can go down to the bank every month and deposit money into the bank to save for your future. That's future value. You can also go down to the bank and make a payment every month to pay off your house, or to pay off your car, or to pay off a student loan. If you are making payments to pay down a loan, that's present value. That is present value. So, if you are making payments, you're going to use one of these 2 new formulas, future value or present value. If you are saving to accumulate, it's future value. If you are making payments to pay down a debt, a mortgage, a car payment, whatever, that is present value. Okay? All right. So, in our problem, first of all, I think we're saving for the future. I do not have these formulas memorized, so I have to write this down. You don't need to memorize them either. I'm on video saying that, so you can hold me to it, but we'll give you these formulas. You don't need to memorize them. All right, so this is the future value formula. This is the one where we're saving for the future. So where's the problem? This is number 7. R is the payment amount. R is the payment. So she is making a $500 payment. Now, I is the interest rate divided by the number of times the payments are made. So she is making a payment every quarter, and it's 7.88 annual, so we're going to take 0.0788 divided by 4. That is her interest rate. That is the I right here. So make notes, make notes. So 1 plus 0.0788 divided by 4, because we are making payments 4 times a year. That is kind of like your K thing was here. It's your interest rate divided by your K. That's exactly what this is. All right, now I got to raise that to the nth. Now, N is the number of payments that I am making. So we're going to do this 4 times a year for 20 years. So N is 80. And then the denominator is the same I you had up here, so it's 0.0788 divided by 4. So in this formula, R is the payment amount, I is the interest rate divided by how many times it's compounded, N is the number of payments you're making total. So remember, it's 4 payments a year for 20 years. All right, now we just type it in. We want to know what is the future value of that account. We just have to type that in. Now, it is kind of hard to type in the first time. Once you get the hang of it, it's easy. But I like to, this is my personal preference, I like to type in my numerator here. So parentheses, 1 plus 0.0788 divided by 4, close parentheses, raised to the 80th minus 1. So I like to type in my numerator, and I type it in exactly the way it looks. So I'm checking my calculator to make sure it looks just like it does up here. Now, I need to divide that by this. Please put that in parentheses. Divided by, parentheses, 0.0788 divided by 4. So now we're going to take that and times it by 500. So she will have accumulated $95,483.39. I wish you were here with me so you could be double checking my math. I'm quickly typing it in again to make sure. I get the same thing. I did. Yep, so that's the answer. If you didn't get that when you typed it in, try again. But the key thing here is, if you're going to divide by this, make sure you have that in parentheses. So it divides by that fraction. All right, now number 8. Carlos purchases a new pickup truck. What are the monthly payments? Highlight that word, payment. The minute you see the word payment, you know you're either using future value or present value. So what are the monthly payments for a 4-year loan with a $2,000 down payment if the annual interest rate is 2.9%? Okay, now think about this. We're making payments. It's either future value or present value. This time, Carlos is making payments on a loan. He is making loan payments. That is present value. He isn't saving for the future. He has a present value of a loan right now, and he's trying to get rid of that loan. He's trying to pay it down. So let's see what go. Oh, let me write the formula down first. Present value. All the letters mean exactly the same thing in this formula. So we're going to work it the same way. Oh, wait, I lost my page. Where am I? Okay. All right, here we go. Carlos purchased for $18,500. What are the monthly payments for a 4-year loan with a $2,000 down payment? Okay, now, R is the amount of payments, so that's what we're trying to figure out. The present value of his loan, the present value of his account is $16,500. I am assuming you guys understand what a down payment is. Carlos purchased a truck for $18,500. So when he went down to the car lot, The guy said it's gonna cost you $18,500. Carlos had $2,000 to put down. So he only had to borrow this much. So 16.5, this is his payment amount. We don't know what that is. We're solving for it. So we have 1 minus 1 plus. Okay, the interest rate is 0.029. He is making monthly payments. So his interest rate, his I, is 0.029 divided by 12. Negative, that exponent's negative, but it means the same thing. Remember, it's the total number of payments. So he's making monthly payments for 4 years, so negative 48 over 0.029 divided by 12. Now, these formulas are crazy looking for sure, but basically, think big picture, you're gonna get R by taking that and dividing it by this bracket. Would you agree? You're gonna get a number here, and you're gonna divide it over here. So I'm gonna figure out what this is first. So just like before, you do it however it works for you. I like to type in my numerator. So 1 minus parentheses, 1 plus 0.029 divided by 12, close parentheses, raised to the negative 48 equals. So now I have my numerator. Now I'm going to divide that by parentheses, 0.029 divided by 12 equals, and now I have this number right here. I've got 45 point something. So this right here is 45 point something. So I have to divide both sides by that. So I'm going to take $16,500, and divide it by second answer. And my payments are going to be $364.49. So again, assuming I got the right answer, this is what you're shooting for. So if you didn't get that first time, try it again. If you still didn't get it, I probably made a mistake. Check with your neighbor. All right. Let's look at number 9. I don't know if I'm going to make it through all these guys, but we hit all the formulas. We've done all the formulas. Let's try number 9. Megan is the trust officer for an estate. If she invests $15,000 into an account that carries an interest rate of 8% compounded monthly, how long will it be until the account has a value of $45,000? Now I want you to read that again, because then you got to decide on which formula to use. Because even if you don't have to memorize all these formulas, you need to know which one to use. So which one do you think it is? I hope you're saying this. We are compounding monthly, and we are not making payments. Megan is taking a chunk of money, $15,000. She's putting it in the bank, and eventually it's going to be $45,000. No payments are being made. Now you might say to me, but Mrs. Ford, she's saving for the future. Yes, she is. But she's saving for the future with a lump sum. She is not making regular payments into the account. Okay? So it's this formula right here. I'm going to leave those up there so I don't have to write them every time. All right, so here's the formula. So what have I got going on here? She's going to invest 15 and end up with 45. So 45 equals 15,000. 1 plus, what's my interest rate? 0.08. Divided by how many times a year are we compounding? It says monthly, so that'll be 12. Raised to the 12 times, how long will it take? 12 is the number of times we're compounding. T is the number of years. Don't know it. Look where that variable is. We're going to need logarithms, aren't we? First thing we're going to do, though, is divide by this 15,000. So it looks like 3 equals 1 plus 0.08 divided by 12 to the 12t. This is exactly like the one we did earlier. Now, I don't like to round off, guys, so I know you might want to do 1 plus 0.08 divided by 12, and we can change it to a fraction if that makes it easier. I just leave it like that. Don't round it off. So whatever you do, don't round it off, because we're trying to keep this as accurate as we can. So that's something. I need to figure out what t is. So I'm going to log both sides. That will pull that exponent off. And now how am I going to get t by itself? I'm going to have to take the log of 3 and divide it by 12. Okay? And then take whatever that is and divide it by the log of this. So, the log of 3 divided by 12. All right, that's step 1. I divided by my 12. Got that taken care of. Equals, okay. Now I'm going to divide that by the log of 1 plus 0.08 divided by 12. And it looks like it's going to take 13.78 years. 13.78 years to basically triple her money, because she's going from 15,000 to 45,000. Take about that long to triple her money. Number 10. What interest rate, compounded monthly, is required for an $8,500 investment to triple in 5 years? Well, it's essentially the same problem, guys, except the variable's different. What interest rate is required for $8,500 investment to triple? So what's 8,500 times 3? 25,500. I want to know what interest rate. We are compounded monthly, and we're going to do it for 5 years. So our exponent is 12 times 5. This is the compound interest formula. A equals P, 1 plus R over K to the KT. No payments are being made. That's it, right there. So I'm going to divide this over, and I'm going to get 3. Now I need the 60th root, or raise to the 1/60th power. Whatever you know how to do on your calculator, we're going to 60th root or raise to the 1/60th power, and that's going to get rid of that radical. So I have a decimal now, 1.018 something right here. So I'm going to subtract 1 from it and times it by 12. And whoa, the interest rate is 22.2%. That's a pretty high interest rate, but it actually kind of makes sense because we're trying to triple our money in 5 years. And over here, it took us 13 years, almost 14 years, to triple our money at 8%. So if you want to triple your money in 5 years, you're going to need a significantly bigger interest rate to do that. So it's a big one, but it makes sense. Okay. let's do number 11. Amy contributes $50 a month into the bond fund and earns this much interest. What is the value of her investment after 25 years? Okay, are you paying attention? Have I bored you to death? We're paying $50 a month. Amy is making payments every month. It's not like this problem where we gave them $8,500 and then walked away. No, she's giving up $50 every month. Which formula is that going to be? It's one of these because she's making payments, and these are the payment formulas. So which one is it? Future value. Amy is saving for the future. What is the value after 25 years? Okay, here we go. What is the value? Her payments are $50 a month. Remember, R is the payment. The interest rate is 0.0726, and we're doing it every month, and we're doing it for 25 years. So 25 years at 12 times a year, that end value is 300. In these formulas, this n is the total number of payments. So monthly, 12 times a year, 25 years, 12 times 25. And then we're dividing by 0.0726 over 12. No logarithms necessary. This is a plug and chug. You do it however you want. We'll see if we come up with the same answer. $2,211.46. I hope that's what you got. I just got it again, so I think that's the right answer. All right, number 12, just about done here. Number 12. Jendo obtains a 30-year house loan with an APR, with an interest rate of 8.75%. What is the monthly payment? She's paying off her mortgage, so the monthly payment, how much is her loan? $86,000. What is her monthly payment? Our interest rate is 0.0875. We are making monthly payments 12 times a year. We're doing it for 30 years. So 30 times 12, that's 360 payments. And remember, in this formula, it's negative. So this is 30 years of 12 payments a year. That's how many house payments she has to make. All right, and then we're going to divide by 0.0875 divided by 12. All right, this is another one of those like the last one we did where we're going to type this in, but to get our payment amount, we're going to have to divide 86,000 by that. So we got to figure out what this is first. So 676.56. I'll check that again just to make sure. Yep, I think that's right. Okay, I'm going to skip number 13. I think you can do it now. It's a monthly payment problem, so it's just like these. Let's look at 14 because it's a little bit different. 14 and 15, if you read them, these are not money problems. Okay, obviously, they're not money. They're more nature problems. You know, bacteria, radioactive elements. They're like environmental nature type problems. When your problem involves a natural situation, it's always the continuous growth formula. It's always the continuous formula. These other formulas are financial. These are used for money exclusively. Making payments, having interest rates, you know, those are money problems. This formula can be used for money. We did one. But it can also be used for any kind of natural growth. It is often called the natural growth formula. So if we look at number 14, it says, find the growth constant. That's like the interest rate in a money problem. That's the growth constant. For a strain of bacteria that grows from 123 to 4, 5, 6, 7, 8. So we're going to end up with 4, 5, 6, 7, 8 if we're starting with 123, and we're going to let it wait 10 hours. All right, now this is another difference with this formula. In the money formulas, your time is always measured in years. But in a natural growth situation, time can be measured in anything. Minutes, decades, years, anything. So we have, what is this one's in hours, okay? So whatever growth rate this is, it's gonna be not like 3% per year, it's gonna be 3% per hour, whatever you get. So we need to solve for R. So the first thing we'll do is divide. And I'm not gonna actually divide this because I'm pretty sure it doesn't come out evenly, and I really don't want round off in my problem. So I'm just gonna leave it a fraction. It's fine. Your calculator will handle it. It's fine. Now I need to get this R right here. I need to get that guy right there. So I'm going to take the logarithm of both sides, but because an E is involved, I'm gonna go ahead and take the natural logarithm. Now you guys know that the base of the logarithm makes no difference. So you could log both sides. You could log base 12 both sides. It really doesn't matter. Use what's most convenient. And when a problem already has an E in it, this is most convenient because ln E is cancels and we've got 10R over here. That's all we've got. So the answer to the problem is going to be ln, the natural logarithm of that ugly fraction. So ln 1, 2, 3, oh no, 4, 5, 6, 7, 8 divided by 1, 2, 3 divided by 10. So your interest rate is a big one. R is I call it an interest rate. Your growth rate is a big one, 0.5917. Just double checking to make sure. Yep. All right, and then that last one. Oh, I gotta go. You gotta go. We all gotta go. Last one. Find the half-life of an element which decays from 2.4 grams. So I'm going to use my same formula. It's a natural growth. Now I know it's decay, but decay is negative growth, so it doesn't matter. We're good. So I'm going to use this formula. And it says I go from 2.4 grams, that's my starting, to 2.1 grams in 11 days. So remember, this is what you start with. I started with 2.4, I ended with 2.1, and it took me 11 days. Well, this one's just like that one, so I'm going to have 2.1 divided by 2.4 equals e to the 11r. So I'll ln both sides. So ln that fraction equals 11r, so I'll just divide by 11, and that'll give me my r value. So ln 2.1 divided by 2.4, and then divide that by 11. Did you get an R value that's negative 0.012 something? Does that make sense? Yes, because what is R? R is the growth constant. And when a population or whatever is getting bigger, R is going to be positive. But what happens when your amount is getting smaller? It's decaying, negative growing. Now, that is not the answer to the question. Did the question say, find R, find the growth rate or decay rate? No, the problem said, find the half-life. So I want you to go back to the problem. I don't want to know, I don't want 2.4 to go down to 2.1. I want 2.4 to go down to 1.2, don't I? If I'm half-lifing. Now the problem is, I couldn't start with this because at the beginning of the problem, I didn't know how long it took for that to happen. That, by the way, is the half-life right there. That T is the half-life. I didn't know how long it would take, and I didn't know what the constant was. Do I now know my constant? I do. Now I know what it is. It's sitting right here on my calculator. So I'm going to divide by 2.4. So that will give me 1/2 equals e to the RT. Now I know R. I got it, but I'm not going to put it in yet. I'll ln both sides. So ln 0.5 equals RT. So the half-life is ln 0.5 divided by that. So ln 0.5 divided by second answer, and the half-life is 57.10, basically, 57.10. And I need a unit on that, days. So it took 11 days to go from 2.4 down to 2.1. But it's going to take 57 days to go from 2.4 down to 1.2. All right, gang, that's it for me. Hope you're having a great day.